You are given an array, and in one operation you can select any window of size at least k and delete the kth smallest element from that window. In the example that you see on the screen, if you take k is equal to 3, then you can notice that you have selected a window of size 4, which is allowed. And what is the third smallest element? So this is the first smallest, second smallest, and the third smallest element. So you can delete one copy of the third smallest element, either this copy or this copy, and then concatenate the remaining number. So this is the sequence that you will get after deleting one copy of 2. So you are allowed to do this operation as many times as you want, but you have to make sure that each time you are selecting a window of size at least k and you are only deleting the kth smallest element. You have to find out whether doing this operation any number of times can result in an array which is a palindrome. So how do you solve this problem? Take a minute to pause this video and think of a solution by yourself before proceeding to the remainder of the video. So if you try to solve it on paper, you will see that you will eventually get stuck. There is no way out for you to come up with a strategy that you can claim as optimal, because there could be a lot of ways to delete some entries. So we need a clear thinking process that can help us guide towards the solution. So what is the first thing that we know about palindromes? That they are mirror images. That is, if you look at this part ABCD, it is mirrored on the right hand side as well. So one thing is for sure, that the final array will contain elements with even frequency only, and it can contain at most one element with odd frequency. So this is just some observation about palindromes, but it doesn't actually help us in this situation. Like, okay, even with this observation, what exactly do we do? How do we figure out which elements to keep, which elements to delete? How much frequency should we keep? How much should we delete, and so on. So this is a category of problems known as ad hoc problems, even though you will see that after you have done some simplification, this problem can be solved via some standard techniques. But to reach that stage of simplification, you have to make some set of observations, and these kind of observations are what is the most important in today's meta of competitive programming. So we'll look at some of these observations and how you can arrive at the solution step by step. So if the problem is talking about the kth smallest element, what does your intuition tell you to do? So you might consider the sorted array, because the kth smallest element in a sorted array is nothing but the element that is present at the kth position. So suppose we sort the entire array. In this problem, you are not allowed to sort the array, but since we are not able to make any progress, it doesn't hurt to think what would the situation have been if the array was sorted. Then if this is the kth smallest element, and let us label it as v, then you can see that there are some elements on the left hand side, I have colored them as red, and some elements on the right hand side, colored them as green. So in this array where everything is sorted, do you notice any special properties about the red elements or the green elements? So one thing that you can immediately notice from the green elements, that all the green elements, they can actually be deleted from the array if you really want. Why is this true? Because suppose if you want to delete this element, then you can just consider this window, and the size of this window is exactly equal to k, because this is the kth smallest element. So you remove one element from the window and add one element to the window over here. So this will now be the kth smallest element, and you can delete this. After you have deleted this green box will vanish from here, and then this will get appended over here. So you can repeat the same process. So this means that if you want to, you can delete the entire green elements on the right hand side if the array was sorted. We have to remember that this condition is only valid if the array is sorted. Now, what about the red elements on the left hand side? Is there anything special about it? So you will realize that the red elements hold an interesting property that if the array is sorted, then nobody can delete these elements. Why is this true? Because there will be a total of k minus 1 red elements and then the last copy, which is v. So no matter what window you select, first of all, you cannot select a window that is smaller than k, right? You have to select a window size that is at least k. And if you have selected a window size at least k, for any of the red elements to be deleted, it means that if red is going to be deleted, then it means that there are k minus 1 elements smaller than it. But if that was the case, why are those elements not present over here? Those elements cannot come from the right hand side. So this means that all the elements on the left hand side, they are protected. Nobody can delete them no matter which window you select. Because if you select a very big window, then you might end up including almost all the red elements. So the kth smallest element will always be either equal to this or something from the right hand side. So green elements will always be deleted first. So that is why we have this conclusion that if you want to, you can delete all the green elements, but even if you want to, you cannot delete any of the red elements except maybe this last element, because this is the kth smallest element, so of course you can delete it. But if you consider all the values that are strictly less than it, then you can definitely not delete it. Now let's go back to the unsorted array case, the original problem, and this time the array is not sorted. But notice that the problem said that you can do this operation as many times as you want. So why are they not asking you to find the minimum number of operations? Why are they asking you to do the operations infinitely many times if you want? So maybe the intuition is that they want you to do this operation a lot of times. So they might want you to do a lot of deletions. And we have already seen in the sorted case, it's possible to delete all the green elements, but only in the sorted case. But is this actually true for the unsorted case as well? So assume that the array is unsorted, then locate all the red elements. So what are the red elements? Basically the ones that are on the left hand side of the kth smallest element. And suppose you have placed them over here. This is the first red element, second red element, and third red element. Now you can notice that even in this array, it is possible to delete all the red elements, even if all the green elements, even if the array is not sorted. Why is this statement true? Because suppose you want to delete this green element. How do you do this? You just start from here and then you go right and you keep on adding red elements to your window. Now the total number of red elements that you will add, that will be less than k, right? Excluding the last copy of v. Let's assume that. And if the window size is not becoming greater than k, then you keep on expanding on the left hand side as well. Once you do that, the window that you have created, we have already concluded earlier that no matter what window you create, since there are less than k red elements, since there are less than k red elements in the original array of the sorted version, then no matter how big of a window you create, if you create a very big window, then you might end up selecting all the k red elements, and in that case the kth smallest element will be a green one, so you can delete this element. Even if this element is not the kth smallest element, this element might be, or this element might be. But one thing you can be sure, that no matter what window you select, all the green elements will always be deleted first before the red elements. So therefore, if you want to delete, you can still delete all the green elements from the unsorted array as well. And all these observations lie on one simple fact, that if v is the kth smallest element, then no matter what, if v is the kth smallest element of the entire array, then no matter what window you pick, there are only k minus 1 elements that are smaller than v. Therefore, no matter how big or a small of a window you pick, as long as you ensure that the window size is at least k, which is given in the problem, then you can guarantee that green elements will always be the first ones to be deleted. So if you repeat this process as many times as possible, you will be able to delete green, then the second green, then the third green, fourth green, and so on. So this manner, this sorted and unsorted array case, it is not entirely different. And now you can see where the intuition for this originates from, because in the unsorted array, in the sorted array case, it was very easy to see that you can delete the right half if you want to, but then we kind of followed the chain of reasoning from there, and we concluded that even in the unsorted array case, you can delete everything on the right hand side if you really wanted to. But now the question is, why would we want to delete all the green elements? So, like, what's the benefit for that, right? In the unsorted array case, we saw that we can delete, but doesn't mean that if you can delete, you have to delete, right? So what is the intuition behind that? Like, should we even be deleting them? So one thing you'll realize that in the first slide, we discussed one important fact about palindromes, that they are mirror images of each other. This means that these elements are less than or equal to V, and these elements are greater than or equal to V, right? So if you want to make a palindrome which is very big, then if you keep one copy of a green element, then you also have to keep another copy of a green element over here. So if a palindrome exists where you have one copy of green element over here, one copy of green element over here, you might as well delete these two elements because it is possible to delete them. And then you will still retain a palindrome with all the red elements only. And the reasoning behind this is, if this is 1 to V and this is the right half, then if you are deleting the entire half, you only have to create a palindrome with these set of elements. Why? Because cross combination does not happen in a palindrome, because if an element 3 is available over here, it it can only be paired with a different 3 from the left hand side. So right hand side does not interact with the left hand side. So this statement is true, but not all the times. And what is the case where the right hand side does not interact with the left hand side? And that case is the last element, which is the V, because some copies of V might exist in the right hand side. So you might not want to blindly delete them, because you might need it to fix something over here. Why? Because some copies of V's, multiple copies of V can exist on the left hand side, and some copies of V can also exist on the right hand side. So for now, if you just consider the right half, if you just consider the green elements as all the elements strictly greater than V, then you can be 100% sure that this strategy is correct. Why? Because all the elements that are strictly greater than V, either you maintain two copies and then you have the headache of tracking a very big list, or you delete these two elements because it's possible to delete them, and then you create a palindrome from the left half only. Now, one thing that you might wonder, that okay, if we greedily delete all the elements from the right half which are not equal to V, then will it not create any issues with the ordering? Like if you had, like let's say if you had this 3, 3, 1, 2, 3, or let's say you have 2, and let's say you have 1 over here. So then you might wonder, okay, if you have deleted all the copies of the right hand side, all the green elements, then this 3 is not being able to match with this, and this 1 is not able to be matched with this. What if you had an additional element from this part, that you could insert somewhere so that all the elements get shifted to the right. So if you could do something like 2 3 1 1 2 1 3, and maybe you could insert something over here or over here that could shift everything and make the entire thing a palindrome, maybe that would have helped, and in that case your strategy of deleting all the right half might not be valid. So even though this idea looks correct that maybe keeping the elements of the right half might be a good decision, but if you think more about it, it actually doesn't influence any relative ordering that you are thinking of. Why? Because if you want to retain one element on the right half, you also have to maintain the other element of that right half over here. So this doesn't really shift the order of the elements that you want to shift, because you are inserting one thing over here, but then you are also inserting another copy over here, because you have to make the entire string a palindrome. So that's why elements from the right half cannot help the elements from the left half, except when the copies of this element is present. So that's why you can conclude that if the answer, so the answer will of course be a subsequence, right? You are just, if you have a1, a2, a3, etc. So you are just deleting some elements and then concatenating the rest. So it will be a subsequence. It means that if you have a subsequence where some of the elements are greater than v, you can repeatedly delete all the copies that are greater than v, and you would still have a valid palindrome. This means that we just have to solve the problem when all the elements are less than or equal to v. So this is the modified version of the problem that you would like to solve. That is, given an array containing elements that are less than or equal to v, can you make it a palindrome such that you are allowed to delete some elements, but the final length should be at least k minus 1, because you cannot select any window that is less than k. Now, in this reduced version of the problem, think about which elements can you realistically delete. So right now we have removed the half right hand part, which is the green part. So all that is remaining is the left part, which is the red part. But remember that we told you earlier that nobody can delete any of the red elements. Why? Because they are strictly less than v, right? But in this array that you have retained, although I have labeled everything in red, some of these copies of v that you have retained might have come from the green part, which were supposed to be deleted. And even on the even on the red part, you can see that no matter what window you select, the first k minus 1 elements, they are always protected, because there is at least one element that is greater than v, that is greater than this element, which is v, and then you have added multiple copies of v in between these, right? So no matter what window you select, the kth smallest element will always be v. So take a minute to pause this video and think about why the kth smallest element in this version of the problem will always be v. So here we are claiming that in this version of the problem, you can only delete the copies of v. You cannot delete any other elements. And why is that argument true? Because these elements are protected by who? By this copy of v. Because no matter what window you select, no matter how scattered these elements are, even if these elements are scattered across the array, then you might have to select a very big window. But if you select a very big window, then as soon as the window size grows to k and there are only k minus 1 red elements that are protected, then the kth smallest element will be equal to v. So this means that you can delete any copy of the v that you want. And why do I say you can delete any copy? Because if you want to delete the copy that is located over here, right, then you can simply start the window from here and then keep on expanding the window until you have k elements, and as soon as you have k elements, you know that the kth smallest element will be equal to v, and you are allowed to delete any copy from the window. So you delete this element, and then you repeat this process. So you are allowed to delete any copy, but there is a constraint. What is the constraint? That you should not delete so much that the final length becomes less than or equal to k minus 1. So we have to solve this reduced version of this problem. So just to formalize this here, this time you are given an array that contains elements that are less than or equal to v, and this time you are only allowed to delete a subset of elements that is exactly equal to v, and you have to make it a palindrome. So you have to report whether creating a palindrome is possible or not. Now, how do we do this? So this is a classic two-pointer approach wherein you start with the last two elements, and right now assume that all the elements are less than or equal to v. Now, if the last two elements, if they are equal, like suppose if they are 2 and 2, then of course they will not affect the answer, right? And anyway, you cannot delete them because x is less than v, and they will also not affect the answer. So you increase your left pointer to here and you decrease your right pointer. What if the last two elements are v and v? So they will also not affect the answer because they are also palindromes, so they are also good. But should you delete them or should you retain them? So your intuition might tell you that you have to retain these elements, and this is kind of a greedy strategy of retaining the elements when the last positions match. But why is this greedy strategy actually correct? It is correct because if you retain this element, then you have more breathing room for this particular constraint, that is your length has to be greater than or equal to k minus 1. So if you keep multiple copies of v around, it will help you delete other copies of v that you want. But if you even if it is matching, and then you decide to delete both the copies, then your length has decreased from x to x minus 2. So it will make it very difficult for you to delete the future copies if you want. So if keeping it does not affect your answer, because these are already palindromes, so might as well keep it, right? So this is the greedy strategy for this problem. Now, what if the endpoints do not match? So suppose if this is v and this is x, so these endpoints do not match, then of course both of them cannot be retained in the final array. But of course we know that x cannot be deleted, because in this version of the problem you can only delete v. So you delete this element, you delete one copy, and then you increment your L pointer. Same situation over here. If it is x and v, and you know that you can only delete v, so you delete this and you decrement your right pointer, because you have to find a match for this x. If you are not able to find a match, then we will not be able to create a palindrome. And finally, if these last endpoints do not match, then there is no way to fix them. Why? Because you can only delete the copies of v inside this inner box. So if x and y are not matching, there is no way that changing the inner elements can fix this. So once they match, then you delete these two elements and your problem essentially reduces to that same problem, but on a reduced space. So you keep on doing this count, and every time you encounter a situation where you have v comma x or x comma v, you delete that v, assume that you can always delete it, and you collect the count of v's that you have deleted. So what is the length of the final array? So you started with this length, the length of the new sequence that you were given, and you have deleted this many copies of v. So the final length is this. So if this length is satisfied, then your answer is yes, else your answer is no. And why is this condition enough? Because here we have tried to delete as small or as few copies of v as possible, because when v and v were matching, we did not delete them. So we did not delete any v unnecessarily. And in this situation where v and x were not matching, then we had to delete it. We had no other choice. So this means that we did our best that we could do. And even after doing our best, if we are not able to make the final length at least k minus 1, then the answer is no. Otherwise, the answer is yes. So in this manner, you can see that using greedy and 2 pointer, you can solve the problem. Now, one thing that you might again still wonder is this length constraint, right? It is becoming the bottleneck, because this is the one that decides if the final answer is a palindrome or not. So then again, you might again have doubts that is this length constraint too restrictive? What if we had kept the green elements around? Would it have helped us with deleting more elements, more copies of V? So again, I think I already discussed on this part, but I'll just reiterate again that keeping extra copies of the elements from the right hand side will not have affected the answer. Why? Because we kept all the copies of V and we deleted only the elements that were strictly greater than V. So if you kept more elements around, then you would also have to keep its matching pair. But if you had to keep its matching pair, then you would have constructed an answer where x is over here and x is over here, and both of them are strictly greater than V. So anybody could have constructed the same answer by deleting an x from here and deleting an x from here, because it is allowed to do so. So that's why this simplification that we had done earlier, that let's delete all the elements from the right hand side, that was that might not be obvious why that was the correct strategy, but in retrospect you can notice that it was actually the correct strategy. And even if you have not done, even if you wouldn't have had done the simplification, it wouldn't have affected the answer part over here. You would still have to delete as many copies of V's as you wanted from this greedy algorithm. Finally, let's look at the code. So first of all, you sort the entire array and then get the kth smallest element, which will be equal to b of k. So here we are just applying a fancy trick where we are decreasing k by -1, so that you don't actually have to track b of k -1, because b of k -1 will be the kth smallest element if you consider zeroth based indexing. But that's fine. That's just a fancy trick. Then you initialize your left pointer here and you initialize your right pointer over here, and then you check if the endpoints do not match, which is like either you hit this case v comma x or x comma v, or you could also hit this case x comma y. So if the endpoints do not match, then one of these has to be equal to the value v. So either v comma x should happen, so this case is listed over here, or x comma v should happen, so this case is listed over here. In the last case, the answer is no, right? So that's why we break early. And depending upon that, if v comma x is happening, you increment your L pointer from here, or if x comma v is happening, you decrement your R pointer and you increase the count of deleted elements. Number of removed elements, you increase the count. Otherwise, if the endpoint does match, like if you hit this case or this case, then you can simply keep on moving forward and backward from the right pointer. Why? Because you want to maximize your chances of deletion of the inner elements. And how can you do that? By not unnecessarily deleting elements when you don't need to. And finally, you check the number of elements that you have deleted and the final window size that has to be greater than or equal to k minus 1. But here, since we had already decremented k by -1 just for a fancy trick, that's why you see this condition here. So just so you don't get confused, I'm explicitly mentioning that. So this is one problem where you could see that there was no playbook to solve this problem. When you saw this problem for the first time, it's absolutely possible to get stuck on this because you don't know where to even start. So in this video, I wanted to show you how to start thinking. And since you were confused, you could at least start with, okay, if it is talking about the kth smallest element, maybe it has to do something with sorted. And if it has to do something with sorted and they're allowing a lot of operations, maybe we might have to delete a lot of elements to simplify things. And then we saw that sometimes it might not be obvious why deleting the entire half is still a valid strategy, right? How does it not change the optimal answer? So some of you might just assume that, okay, sure, well, if we can delete the right half, let's delete it. But things are not always this smooth, right? Because once you delete it, it might have consequences. But in this problem, I showed you that there are no consequences if you delete this. And all of these was made possible because of the properties of palindromes, that they are mirror images of each other. So why maintain the headache of maintaining the entire number line when you could just maintain these set of elements and then you can try to match them against this, because one element from this set cannot be matched from one element from this set.